Okay, now we start integral vector calculus. And the first thing is the work integral, which is a particular type of line integral, but it's the only type of line integral I cover in my course. Here is the work integral. F is a vector field. Remember, a vector field at every point in space, there's a vector associated with it. That's what all these little arrows here. Integral is over a curve or a path. This line is through that vector. R is the position vector to that curve. So F dot dr, even though F and R are vectors, the dot product is a scalar. This is just an integral over a single variable. So F is a function of x, y, and z, the coordinates, and R is always x, y, z, the coordinates. And since it's a one-dimensional creature in two or three-dimensional space, you can parameterize the position with some parameter. We'll call it t for now. So then dr dt would be this, or dr is just dx, dy, dz. R is x, y, z, dr is dx, dy. If you take the dot product and that, with that format, F is p, q, and r, where each of p, q, and r are in turns functions of x, y, and z. That dot product, f dot br, is going to look like this, which means the work integral could end up looking like this. Which looks kind of strange if you're new to this. It's a single integral symbol. There's a dx, a dy, and a dz in it. Every semester, there's at least one student who tries to split this up by adding up three different things. That's a big no-no. That's not what it is. This is actually an integral over a single parameter. And that's the whole trick of how you evaluate these guys. You parameterize in terms of a single parameter, and then you integrate normally. You'll see that there's several ways to skin a cat with these things. So the easiest way to go about this is to just go through examples. Well, let's say here's our integral, where the curve is defined. It explicitly parameterizes it for us. It tells us what x, y, and z are as functions of t, and it tells us as t goes from 0 to 2. So the vector field, p, q, and r, remember, but here p is just y, q is just c, and r is just x. Here's what the vector field is in terms of x, y, and z. X, y, and z are in turn functions of t. Just make all these substitutions. Everywhere there is y is t cubed, d is 5/2 t squared, etc. So that's what you get for f. R is always x, y, z. Substitute in x, y, and z are in terms of t, you get that. What's dr then? It would be 3t squared, 5/2 t, all times dt. Now I have the f, I have the dr, I take the dot product, like this. That's what you integrate normally from 0 to 2, because that's where they told you where t is. At this point, it's a normal integral, and I won't go through it. We'll just try to get to this point with these examples where it's a normal integral. Another way to do that same problem is by direct substitution. Everywhere there's an x, you put in 3t. Y, you put in t cubed. Okay. What do you put in for dx then? 3t. Put in for dy. 3t squared dt. This integrand then, by direct substitution, becomes this, which then simplifies to this. At point, that's what you integrate over, again from 0 to 2. At this point, it's the same integral as before. Integrate it normally. Here's another one, just slightly disguised. Instead of giving you x and y directly, it says here's what r is in terms of linear combination of the standard basis. But that tells you that this is what x is, e to the minus 2t, and y is e to the t. There's what our r is, meaning dr, I just take those derivatives, minus 2e to the minus 2t. And then f, every place there's an x, I put in e to the minus 2t. Every place there's a y, I put in e to the t. Here's what f is when I make those substitutions and when I simplify. So now I can take the dot product. This dotted with that. There you go, and here is our integrand. That's what we integrate over. It goes from 0 to natural log of 2. I don't think I need to go through this. It's plain old calculus and maybe a little bit of algebra. Oh, how about this one? Oh, you don't see t explicitly, but y is a function of x. That's the curve, in fact. And it tells you it goes from this point to that point. So the parameterization, it's only two-dimensional, just x and y, no z, and it gives you y as a function of x. So you use x as your parameter instead of t. Let's see, r is xy, right? X is x and y is x squared plus 1. So dr is 1 and 2x. X. F, here's our p, there's our q. Everywhere there's a y, we're going to replace it with x squared plus 1. That simplifies a little. Now we take the dot product. This thing dotted with that dot product. What do you get? This, and it simplifies a tad. And this is our integrand that we integrate over. Our parameter is x. So in these points, all we care about is the x coordinate. We're going to integrate from -1 to 2. Those are our limits. And when I gave exams, I would give like 70% of my points on seeing this correctly. Screwed up taking that integral, it was only maybe 3 points out of 10. So this, getting to here is the big step, including the limits. Do the same problem by direct substitution again. If y equals x squared plus 1, dy equals 2x dx, right? So now I just plug directly into the original problem. Every place there's a y, I replace it with x squared plus 1. Every place there's a dy, I replace it with 2x dx. And all the x stuff stays the same. Here we are, it'll be 2x plus x squared plus 1 dx plus x times x squared plus 1, dy is 2x dx. Go. Again, we're integrating over x, so all we care about are the x coordinates to -1 and 2. Those are the limits. At this point, it's a normal integral, and we did it on the previous chart as well. One more example. In this video, let's do one more problem. Here it is, and it gives the path x is a function of y in this case. So let's parameterize in terms of y. Now you might say, you could have said y is the square root of x. Well, it would be plus or minus the square root of x. You got to deal with the plus minus. So let's just keep it this way, nice and easy. Parameterizing y. So let's see. By direct substitution, x equals y squared, which means dx equals 2y dy. Y goes from -1 to 1. You only need the y coordinates, points. So everywhere there was an x, we replace it with x squared. Every place there's a dx, we replace it with y dy. All the y stuff stays the same. And direct substitution, here's what you get. It simplifies a little bit. And at this point, it's a normal integral. I'll save this for next time.